Welcome back to this electronics class. This is going to be our seventh lecture in this academic session. As usual, type your attendance again, and I think I can start my lecture because without delay, we have to complete this topic: potential barrier between the p-n junction calculation. Let me just try to recap what we discussed yesterday. So we have said that when we have a p-type semiconductor and n-type semiconductor joined together, there will be a diffusion of charge carriers. Like on the n side, you have large concentration of free electrons. On the p side, there is a large concentration of holes. So the concentration of holes on the p side is denoted as p subscript p here, concentration of holes on the p side. And concentration of holes on the n side is denoted by this line, which is denoted by this symbol P, and Pn stands for concentration of holes on the on the n side. And here on the n side, we have large concentration of free electrons. The concentration of free electrons is Nn here, which is much greater than the concentration of holes, that is the Pn in the n side here. And on the p side, however, concentration of electrons is much lower than concentration of holes here, which we denote it like Np. And because of the difference in the concentration here, we say that there is a diffusion, and the diffusion results in the formation of the space charge region here, the formation of the space charge region, where on the n side, those pentavalent atoms donate their extra electron to the trivalent atom on the p side, thereby transforming the pentavalent atoms into positive ions here, trivalent atoms into negative ions here. So there is a space charge region. We also call it a depletion layer or depletion region because this region does not have any free charge carriers now, right? And this space charge region results in an electric field in this direction because the positive ions are on the p-n side, negative ions are on the p side. So there is a built-in electric field here. So that means if there is a built-in electric field here, that means there is a potential difference between this and this. So the potential difference between this point and this point is what we call it as a potential barrier, potential barrier across p-n junction, potential barrier across p-n junction. The potential difference between this point and this point, that is the other end of the depletion layer on the n side and the other end of the depletion layer on the p side. The potential difference between these 2 points is called the potential barrier, which we will denote it as a VB, potential barrier between that in the p-n junction. As you see, there is a built-in electric field and there is a formation of space charge region with positive and negative ions. Now, uh, in order to obtain this potential barrier, we need to consider what we already discussed, the diffusion current and the drift current. So let us try to express a diffusion current like this. So I will just take this expression because the derivation of this diffusion current is not exactly within the purview of our syllabus. So the diffusion current, electron diffusion current here, I put a subscript E here. E means the electron diffusion current here. So electron diffusion current is expressed like this. Here you have a negative electronic charge and you have diffusion coefficient of an electron and you have a concentration gradient. So again, as I said, diffusion is due to concentration gradient. So if there is a concentration gradient, there will be a diffusion of charge carriers, and the diffusion of charge carriers will result in current, diffusion current, like I discussed yesterday. So when there is a concentration gradient, And because of the concentration gradient, if there is a charge transfer from one side to the other side, then the net charge transfer in that particular direction will result in what we call it as a current or diffusion current. And here the concentration gradient dN upon dx is taken as positive. Why do we take dN upon dx as positive? If you look at this, we are talking about the depletion region. From the left side, the electron concentration is quite low. But if you move towards this direction, that is along the increasing x value, if you move along the increasing x value, you will see that the electron concentration rises from this to this. The electron concentration rises from this to this within the depletion region. So electron concentration, as you see, it increases with increasing x value. So if you take something like an example like this, if you have something like this, if you have y, if you have x exists here, so what is the slope here? Slope is like this. This is, let's say, your del y, and this is your del x. Now the slope is del y upon del x. Now let me take another curve here. Let's say y, x. Now let's say we have it like this. This change in y is del y, change in x is del x. So here also the slope is del y upon del x. Now we have two straight lines here. One is aligning like this. Another one is aligning like this. Here you see that in this case, with the increase of x value from this point to this point, x value is increasing. That is, del x is positive. With the increase of x value, del x is positive. Y value increases from this to this. So del y is also positive. So del y is also positive. So in that case, the slope is positive. Now here in this case, as you increase the value of x from this to this, increase along this, that is del x is positive. Here at this point, what was del y value? This was the del y value. At this point, what is del y value? Now this is the del y value. Del y value, as you see, it decreases from this to this. So del y is negative. So therefore, the slope is negative. Okay, so just like that, here we are talking about n dn upon dx. So if you increase dx along the x-axis, dn value is also increasing. So dn upon dx is positive. The concentration gradient is positive in our picture here. And what is this diffusion coefficient of an electron? Diffusion coefficient is simply a measure of how easily, it is a measure of how easily electrons can move under diffusion process. How easily electrons can move under diffusion process. So this is actually a temperature dependent quantity. Okay, this is actually temperature dependent quantity, temperature dependent. So you know that at absolute zero, at 0 Kelvin, everything freezes, so that if the electrons cannot move at all, so the diffusion coefficient is also 0 at 0 Kelvin. But if you increase the temperature, those electrons, they can start having certain kind of possibility to move. So if you have a concentration gradient, under concentration gradient, those free electrons will move according to the concentration gradient. And how easily the electrons can move around under concentration gradient is what we define it as a diffusion coefficient. So the electron diffusion current, that is a result of electron diffusion, can be expressed like this. And similar to that, we can express the Hall diffusion current. Here we put a subscript H here, means this is a Hall diffusion current. You know that holes are considered as positive charge because it is deficiency of electrons. And this dH is simply the diffusion coefficient of holes under, this is again a measure of how easily holes can sieve from one valence band, one covalent bonding to another covalent bonding under diffusion process, how easily holes can sieve, right? And here we have taken the concentration gradient. P is the concentration of holes, X is the changes along the x-axis. So how the concentration of holes changes along the x-axis is defined by your concentration gradient here. So the concentration gradient is taken as negative here for holes. The reason is that here on the left side, we have a p-type. In the p-type has a high concentration of holes, but if you move towards the right side, that is increasing x value, if you move along increasing x value, the whole concentration falls down from this to this. So therefore, del p upon del x is taken as negative here. Okay. So in addition to this diffusion, here we have said that we have a built-in electric field here because of this space charge region. Now, under the action of this electric field, electrons and holes also will move. Under the action of this electric field, electrons and holes also will move, as we already discussed. So when electrons and holes move under the action of electric field, we call that motion as a drifting of charge carriers. Drifting of charge carriers when they move under the action of electrons and under the action of electric field. Okay, when the charge carriers move under the action of electric field, we say that there is a drifting of the charge carriers. Now, the drift current, like we discussed before, it is simply sigma. Drift current of an electron is sigma E into E. Okay, here sigma we E in the like last week classes we have defined the conductivity of electrons. N type, the conductivity of N type semiconductor, or the conductivity of electrons. So drift electrons. So this is simply mu E. Okay. E is the C is the electronic charge, N is the concentration, and mu E is the mobility. Mu E, as I discussed before, it is a measure of how easily electrons can move under the action of electric field. How easily electrons can move under the action of electric fields is defined as the mobility of that electrons, those electrons. Okay, so we can define this like this, drift current also. And also again, we can define what we know it as a drift current for holes. Drift current for holes also we can define. And now, considering the two type of current that are possible across the p-n junction, that is one due to diffusion and another due to the drifting under the action of electric field. So the drift current, as we have just expressed, it is written like this. The diffusion current can also be expressed like this. And similarly, for the Hall current, the total Hall current will consist of drift current as well as diffusion current. And you know that in the Hall, the current density is conductivity into electric field. So conductivity of holes is having a positive charge, and concentration of holes, mobility of holes, how easily the holes can move, mu h. Okay, so you can put all these values and you will get the total Hall current like this. As I said, mobility and diffusion coefficient, they are temperature dependent. So at 0 Kelvin, they freezes. So the mobility and the diffusion coefficient is 0. But as you increase the temperature, there's mobility and the diffusion coefficient also will vary according to that. And here, the diffusion coefficient is directly proportional to temperature. Mobility is inversely proportional to temperature. So this relation, the dependency on temperature is given by what is known as Einstein relation. So this is related to thermal energy by this Einstein relation. There is a derivation by Einstein, so we'll not get into that. So this is a part of your thermodynamic course. So anyway, this is what the relation that was proposed by Einstein, regarding this diffusion coefficient, electron or hole mobility dependence on temperature. So kT upon E is known as the mean thermal energy of the particles, like electrons or holes, and this is also known as the voltage equivalent of temperature. So this quantity is given by this. Okay, so uh, also we know that, say, we are talking about a p-n junction here. We are talking about a p-n junction. We just have a we have a p type, we have an n type, and we just put the two type of semiconductor together like this. Okay, so in the absence of any external biasing, this is external biasing. So in the presence of this external biasing, we know that there is a current across the p-n junction. But in the absence of this external biasing, if you consider p-n junction as it is, uh, uh, eventually, as I said yesterday, when there is a diffusion, there will be electric field building up, or the potential barrier that is building up across the p-n junction, and this build up electric field will eventually stop the electron diffusion, or the diffusion current will be cancelled by the drift current. See, the diffusion of electrons has to go from this to this direction, as you see. But if you just put a charge carrier here, under the action, if you just put the electron here, under the action of this electric field, electrons, as you see, this side is having negative ions, this side is having positive ions, electrons will tend to move in this direction. So the diffusion current direction as well as the drift current direction across the p-n junction will be in opposite direction. So when the diffusion continue for some time, and sufficient amount of positive ions and sufficient amount of negative ions are formed here across the p-n junction, those ions will generate sufficient amount of electric field across the p-n junction, such that the electric field will result in drift current to cancel out the diffusion current. So instead of electrons transferring in this direction, because of the under the action of this drift electric field, those electrons will be repelled back, and there cannot be any resultant current across the p-n junction. Okay, so if you take a lone p-n junction without any external biasing, the current across the p-n junction will be zero at equilibrium. Current across the p-n junction will be zero at equilibrium. Therefore, in an open p-n junction, that is without any external connection, the total current will be zero. So total current component of the electron is zero. Total current component of the holes also will be zero. So here you know that electron is current, total electron current is given by this. So unless you apply any external potential source, JE will be zero and JH also will be zero. So if you consider that relation, this is equal to zero, and if you just rearrange this, this is what you will get. And dE upon mu E, using Einstein relation, you can put it as KT upon E, and this is what you will get. Okay. Now, so this is your junction region, and here this side, this part we call it x1, and this side we call it this junction, this the other end of this potential barrier, the other end of this depletion layer we call it x2, the other end of this depletion layer on the p side we call it x1. So if you integrate from x1 to x2, integrate from x1 to x2, x1 to x2, dx will change from x1 to x2. Now here dn is the variable, x is the variable, so integrating from x1 to x2 will be equivalent to, as you see, what will be the changes in n? N is the variable, means n value, that is the free electron concentration will increase from this to this. Free electron concentration at x equal to 1, at x equal to x1 here, at x equal to x1 here, free electron concentration is Np. At x equal to x2, free electron concentration is Nn. Okay, so if you integrate from x1 to x2, n value will change from Np to Nn here. Np is the minority charge carrier, minority free electrons concentration in the p side. Nn is majority free electrons concentration in the n side. So if you do that, n variable will change from Np to Nn, x variable change from x1 to x2, and this is what we defined as the potential difference developed across the p-n junction. We also call it as a potential barrier. And if you do this integration, this will be ln of n. So ln of Nn minus ln of Np, and this is the usual relation for the electric field and the potential. So I think you all know that. Now this is what we arrive at, and from here let us see what the quantities we have seen so far. So Nn, as we know it, it is the concentration of free electrons, in n region, concentration of free electrons in n region. So this is equivalent to, as I discussed in the previous lectures, Nd, number density of donor atoms. Okay. Now Np is the concentration of free electrons in the p side of the junction, in the p side. So if Na is the concentration of acceptor atoms, means Pp is equal to Na. If you revise our discussion, our previous, I think 2-3 lectures ago, we talked about this. So Pp is equal to Na, and this is what we know it as a law of Malas. So this simply says that the product of, see, this is the p-type semiconductor, the product of free electrons and the product of holes is always equal to intrinsic carrier concentration, square of it, square of intrinsic carrier concentration. Np into Pp is equal to Ni square. The product of free electrons in p-type and the product of holes in p-type is equal to square of intrinsic carrier concentration. So we can denote Pp like this, then Np can be written like this. So if you put this value there, Np value here in this relation here, and Nn value also, this is what you will get as the barrier potential. Okay, so this is the potential difference that develops across the p-n junction. So when you form a p-n junction, this is the junction. On the end, this is the p side, this is the n side. On the n side, let's say this is x1. On the p side, let's say this is your x2. Sorry, on the n side, let's say this is your x2. So this region is the depletion region, and in this depletion region, due to diffusion, we say that there is a positive ions formation here. Correspondingly, there will be negative ions formation here. We have talked about this. If you revise your notes or my lecture, this we have talked about it. So there will be a negative ions formation, and these negative ions and positive ions formation will occur, and this will develop an electric field across this junction. So this electric field across this junction will result in potential difference between this point and this point. Potential difference between this point and this point. That potential difference that is across the p-n junction is what we know it as a what is known as a potential barrier across the p-n junction. So how much potential barrier is developed across the p-n junction is given by this. So the potential barrier across this p-n junction is dependent on temperature. So if the temperature increases, the potential barrier increases, and also it's dependent on your acceptor atoms. How many p-type dopant, or how many trivalent atoms is doped per unit volume. This is acceptor atoms concentration, that is concentration in the sense number of acceptor atoms, number of trivalent atoms per unit volume. This is number of donor atoms per unit volume. How many pentavalent atoms are doped per unit volume. So that means if you increase the doping concentration, Na and ND value will increase. So doping concentration increase means you are putting large quantities of trivalent atoms and large quantities of pentavalent atoms. So if you are putting more trivalent and pentavalent atoms per unit volume in the p side and the n side respectively, then the potential barrier that is developed across the p-n junction, which we call it barrier potential, will increase. So barrier potential is something we can control by controlling the doping density, that is number of pentavalent atoms and number of trivalent atoms inserted per unit volume. So like that, this is what I would like to discuss here. So if you have any question here, if you want me to repeat any point, so please feel free to ask, because we have about 7 minutes, so we can discuss, because I don't want to continue to the next topic. The study material is provided to you, so you can go through your study material also. And yeah, I strongly suggest that you start your uh, you start studying the notes provided to you. And also some of you might just assume that just having a soft copy is sufficient. Please don't do that. uh, See, we cannot have an offline lecture or a classroom lecture, so because of that, we are providing all the detailed study material. But in order for you to really understand and to really learn the topic that we are discussing here, you really need to work yourself. That is, take out the notes like in your mobile phone and all. I have provided the notes in the WhatsApp group. But purchase an exercise notebook. So now till today we have finished up to this barrier potential. So starting from the first page in my notes, please copy down everything on your exercise notebook till the barrier potential. Okay, so that while copying the notes, you will read through my notes. And as you read through my notes, if you listen to my lecture, I think you will recollect something, and then you can try to interlink what I discuss in the online lecture and what is written there in the notes. So from there also you might have some queries and some doubts while copying down the notes. Then only you can learn. So if you have certain doubts in your mind, go through the notes and go through my lecture and try to clear your doubts. So if you cannot clear your doubts, you can always talk to me. I can help uh, if you have any problem in understanding any part of my lecture. So if none of you are having a queries, I can stop. But please go through my notes, because this week I thought of like starting a online class test. But the condition is such that many of you are having internet issues. So hopefully by this weekend, that is on uh, Saturday or Sunday, we can have a class test. I'm preparing this thing, MCQ test for you. So up to whatever topic we will cover towards the end of this week, we will have a class test. So please start studying your notes and the lecture. Okay, so I think I can stop if you don't have any queries. Okay, you can leave now. We can start a new topic next class.